Hello, welcome everybody. I'm here to show you how I created those planar reflections you're seeing here on the water. Pay attention to the stones right here. You can see how you can see the parts under the water and the reflections of the trees, which means that yeah, it's all working. You can see the moon over there being reflected, and yeah, you can see the how it all is like mixing the reflections with what's underwater. Uh, you can see also like the code that I created, of course. You can see it for free, you can use it, you can modify it. It's all open source, and you can learn from it. The implementation is not like 100% mine. Actually, this technique is pretty old actually. I just adapted it to work on the built-in render pipeline. And yeah, that's mostly it. So to start off, I think we should start with the theory. Like before I start to talk about the probe itself, the code, and how you should use it on the Unity engine editor, I think it's I think the most important part is to understand the theory behind reflections themselves. How do they work, like in real life actually, because like it's not that complicated, and if you understand that part, then you can translate the whole process into any engine you want, any project, whatever your game is, and of course you can also change it, adapt it to better fit your own games. So I have built this little little game here. You can probably notice that there is a mirror right in the middle here. And well, how do mirrors actually work? You might have like heard it before, maybe in a I don't know, physics classroom when you were a kid or something. Um, the easiest way for you to think about a mirror is to think of it like a window to the same room, but with everything flipped. You just flip the position of everything in the room. And I did that here. Look behind the mirror. You see? I have the same sphere, the same box here, and the mirror is right in between. You might not be able to see the mirror because it's transparent and all. I mean, not really transparent, it just blends in very well. So that's what I did. And as you might have noticed, as I go around, there is not much difference in like what I see in the mirror and what I see behind the mirror. In fact, I can remove the mirror here. See? You can see that the biggest differences are like on the light. The shadows, they turn around. I think that the lit faces on the cubes, they change too as well. So yeah, that's pretty much like the lighting that we can see very well. I think we can see like the sun reflecting here. If I take the mirror away, it's not there anymore. So yeah, this is like in a basic way, this is how mirrors should work. That's what they should show. So how do we go about making a mirror? Well, you can see that just copying the room and turning the mirror into a window doesn't really work that well because of the lighting. So unless you could like translate the lighting, like make a light that just affects the room and a different light that just affects the mirror where everything is flipped, and then you flip the light as well, the directions, the positions of the light sources, everything, that could probably work. But that's not what I'm doing here, of course. And what is it that I'm doing? So, the same way that everything in the room is flipped, what you see is also what you would see if you were in the flipped world. Let's call it the mirror world. For example, if I was here, where should I be in the mirror world? I should be in the same position but relatively to the mirror. like around here. So if I look right here, what the mirror should see is exactly what I'm seeing right now, in this position. So what do? We create another camera, and we position it in a way such that it's always in the mirror world, like flipped in relation to the surface that's reflecting to the mirror. And that's basically what I do. So, how do we go about finding the position of the probe when we only know the position of the plane and the camera? I mean, you'll be the one making the scene, so you will be placing the plane, the mirror somewhere, and you know where the player's position is. I mean, the camera is the player, or somewhere linked to the player, or whatever. You get my point. So, how do we figure out the position of the probe when we know only the position of the plane and the position of the camera? Let's say we knew this vector. What if we could find this vector, the projection of the camera into the reflective plane? If we knew this vector, then it is kind of easy to see that the position of the probe should be the position of the camera plus 2 times the projection vector. Correct? Well, yes, sure. Now let's go about finding it. How do we find the projection vector? Well, let's go about first everything that we know. Again, we already know the position of the camera, the position of the plane, and there is something else, some other vector that we know that I haven't talked about yet, and it is the normal vector. Again, you will be the one placing the mirror on the scene, so there should be some vector that is perpendicular, orthogonal to the mirror, pointing out of it. And that vector is the normal vector. You have to put this vector on the probe. I'll show it later. So, how can we find the projection? Well, let's take a look at this vector here first. Let's see if it rings a bell to you. Yeah, this vector should be equal to the camera position minus the plane position. And looking at this figure here, we can see that this is a right triangle, which means that the projection should be equal to the camera position minus the plane position times the cosine of the angle between this vector here and the normal vector, correct? Which means that the projection's length, at least the length, is equal to the camera position minus the plane position dot vector dot product, the normal. Dot product, if any of you have never heard of it, don't worry, Unity got you covered. You have this function here on vector 3, you feed it 2 vectors and it gives you the dot product. Once again, the dot product is a number, which is why I am saying that it isn't the projection vector, it's just the projection vector's length. However, as I said, the length is just a number, it's a float value, not a vector 3. So in order to get the projection vector, what we need is the direction of the vector in a unit length vector, and then we multiply it by its length that we already know. However, luckily, we already know that the direction of the projection vector should be equal to the normal vector's direction. So yeah, we have here on the screen that the projection vector should be equal to the minus normal vector times the projection's length. Easy so far? Maybe not so easy, right? Yeah, but then again, we have that the proposition should be equal to camera position minus 2 times the normal and the projection length. But wait, it is not over yet. We still have to figure out the rotation of the probe. I drew these colored vectors here to represent the forward and the up vectors. Like, that's how they are represented on the editor at least. The up vector and the forward vector. You can see them on the editor when they are like this, you know. The green vector is the one pointing up, the red vector represents the x-axis, and it's called the right vector because it always points right, it always points to the right. And the z-axis represented by the blue vector, it points always forward. You know, when you rotate an object and these arrows are also rotated. Yeah, I think at least like an easy way to represent rotations is by the position of these three vectors over here. Anyway, how do we, going back to this part here, how do we figure out these vectors? How do we figure out the probe up and the probe forward when all we know is the camera up and the camera forward? Well, again, we have to go back to the law of the mirror. That the distance between all three of these points should be cut in half by the plane, the reflective plane. Okay, let's figure out the camera forward vector first. Looking at this, like, nothing comes to mind, does it? I don't know. Let's make them closer together a little bit. A little better now, right? This is an isosceles triangle, and I guess these two angles away from the plane are equal. But that doesn't mean a lot, does it? The basis of this triangle is also parallel to the normal vector. Yeah, that might help a little bit, right? Let's bring this triangle a little closer to the normal vector. Like this. So, is it ringing any bells to any one of you yet? How about now? Yes, what's happening here is basically that the probe forward should be the camera forward but reflected in relation to the normal vector. That's pretty much it. It's the reflection. If you have ever, like, if you know how to reflect, then good. But if you don't, again, don't worry. Unity has got you covered. Even if you do, you better use Unity's function because it's just much easier this way. There is no math to be actually done. You just have to know this function right here. Again, the idea is that it treats the vector that you're feeding it like a ray of light, and the vector that it returns is the ray of light that would be reflected by the plane that's represented by the normal direction that you also need to feed to this function here. And what about the up vectors? No surprise, they're also, it's just another reflection. It's pretty easy to see. You can move them up there, and yeah, that's pretty much it. Okay, so we can find the up vector, the probe up vector, and the probe forward vector. How can we derive the actual rotation out of these two vectors? Again, Unity has got us covered. We have the LookAt function that all transforms have. And basically what this function does is that you give it a point and an up direction. And then the thing that the transform that you're using it on will be rotated in order that the forward vector will look at the direction on the direction of the point that you gave it, and it will try to match its up direction on the up vector that you also gave it. So it's just that simple. Like, all you have to do is give a direction that makes the forward vector equal to the forward vector that we calculated. How do we give that point? Well, we just we just add the forward vector that we calculated to the position of the probe that we already have. So yeah, let's recapitulate everything, and that should be pretty much all that we have, all that we need to calculate the transform of the probe. We have that the projection length should be the dot product between cam pos minus plane pos with the normal. which means that the probe position should be the camera position minus 2 times the normal vector times the projection length. Okay? Okay. We have that the probe forward vector should be equal to the reflection of cam forward with their normal. The probe up vector should be equal to the reflection of the camera up with the normal, which means that the rotation should be derived from the LookAt function by feeding them the probe position plus probe forward vector and the probe up vector. And that's just it. If you go to see my code right now, that's literally what I do. Literally on this order right here. Okay, let's get back to our scene right here. Let's apply what we learned. So, if we are here and what the probe is seeing is being rendered directed into the mirror, where is the camera and what is it seeing? Well, we should just reflect our position here and our rotation, and this is where the probe should be, and this is what the probe should be seeing. And yeah, it's wrong, right? That's not what's being rendered on the mirror right now. First of all, because from here we can see that there are 2 cubes and 2 spheres. So yeah, the probe seems to be seeing only the cube and the sphere that's in front of the mirror, not the ones behind it. So how am I hiding them? What's going on? Well, in order to explain that, I would have to talk a little bit more about cameras. How do Unity treats cameras? Not just Unity, but like shaders as a whole. Okay, let's talk about the camera frustum. So, the camera frustum is that shape pyramid thing I'm showing on the screen right now. Basically, what is inside that shape will be rendered, and what's not inside that shape will not be rendered. This is basically what it is. It tells the camera what should be rendered and what should not be rendered. The important bits here are these 2 planes that are being pointed to in the picture. The near clip plane and the far clip plane. Every camera on Unity has a value for near clip plane and far clip plane. These values are literally the distance from each plane from the camera. If you put a near value that's like too far away, then things that are too close for you from the camera won't be rendered. Let me show you how the near clip plane ends up working in practice. Like if you get too close to any geometry, you can see that it kind of gets cut like this. This is because the geometry is getting beyond the frustum. It's closer to me than the near clip plane is. Now, let's remember what we were trying to do. So, we knew that the camera was behind the mirror, but there were also more geometry, more things behind the mirror, and these things shouldn't be rendered on the mirror. They're not on the stuff that will be reflected. They're not in front of the mirror to be reflected by it. And we wanted to clip them. We want them to not be rendered by the probe. And yeah, we just found out that naturally the camera has these two clipping planes right here. Could we perhaps make the near clip plane coincide with the mirror? Well, that would mean that the camera, the probe's camera should always be looking directly at the camera. And after everything that we have calculated, like the rotation of the probe, this just can't be possible. We can't do that. So, is it possible for the near clip plane to not be this way, to not be like always perpendicular to the direction, from the direction that the camera is looking? Can't we make the near clip plane look like this? Can't we like tilt it a little bit in any given direction that we want? Well, my friends, yes, it is possible. This technique is called Oblique projection matrix, and it's called oblique because basically it makes the near clip plane a little bit tilted, it makes it oblique. And Unity does that with that function that I'm showing right now. So yes, this is basically it. We need to recalculate the position and the rotation of the camera's probe, and then we need to use this function to make the near clip plane of the probe's camera equal to the reflection plane, the reflective plane. So finally, let's talk about the probe on the Unity editor. I'm on the editor right now here, and you can see that the mirror is working on the editor itself. And yeah, how do I make it? How do I make it work? How does it functions on the editor? Well, just like most things on the editor, you can just create any object. Let's call it probe. And on the add component part, you just click it, and then you go to rendering, and there's this new option here, Planar Reflections Probe. It will show up just if you have this the script, the C# script that I wrote, it will show up on your menu as well. And then this thing here, this menu here will show up. This target texture ID, it's an integer value, and it varies from 1 to 4. It basically tells the probe like there are 4 slots, 4 textures that will be rendered to. Texture number 1, texture number 2, texture number 3, and texture number 4. And this ID here tells the probe which texture you want it to render into. They are sent to the shader as a global variable. This means that you can use them in order to use them. You need to write your own shader, and the pros of that approach is that you can do whatever you want with the texture. You don't need to render it exactly what I did here. You don't need to render this mirror in this way. You could like distort the image, like if you're making water, for example, running water or just agitated water overall, then you would need to distort the image, you know, to make it look like the water is shaking. You could maybe change the colors. You could maybe, I don't know, do some psychedelic stuff. Be creative. So yeah, you have total control of what is actually being rendered. I'm just rendering a texture with the probe, with what the probe is seeing. And what you do is that with this texture is up to you. I'm also only putting 4 textures here because, as you can imagine, I am literally rendering the screen again. And rendering the screen again is expensive, you know. And if you want it to be less expensive, you can just take down this value here, the reflections quality. The quality is basically a value, a float value that is multiplied by that multiplies the resolution. If you set it to 1, then the resolution of the texture that it will render into will be the same resolution of the camera that it's rendering to. Like in this case, I'm rendering to a 1080p monitor here, so it's 1080p as well, because I kept the quality at 1. But if I took it down to like half, then it would become 540p. So yeah, this is a way to make the reflections less costly on the GPU. But yeah, I'd still suggest you to don't have like multiple probes on the screen. Like if you really want multiple probes, then you need to have each one of them rendering to a different ID, because if they overwrite the same ID, then yes, one of them will be lost. Only the second one will be kept. So it makes no sense. So yeah, I'm putting 4 slots here, but if you want more, you can just change the code and add more. It's not a big deal. Here on plane normal and plane position, you have to like manually put in the positions of the reflection plane and the normal going out of the projection plane. This means that putting out a normal can be quite, could be quite awkward if the plane, if the mirror was positioned in a weird way, rotated in a weird way as well. So I'm adding this option here to use the forward vector as the normal. Like this here is the probe, the object, and if I set this as true, then it will completely ignore what I write down here, and it will use this blue arrow here as the normal. So yeah, this is a very good way. Like if I wanted this new probe here to render to this mirror that's already on the screen, then yes, it's already pointing in the right direction. And yeah, then I have the far clip plane here, and another option here, render background. It's just so if you want the reflections to catch the skybox, basically. Like sometimes you have on the camera that you're rendering, you have a different skybox, and sometimes you don't have a different skybox. Sometimes you don't want it to have the same skybox. Then you just toggle this option off, and it's not gonna render the same background as the main camera it's rendering from. That's actually rendering the screen. And then I have this render in editor part here. That's basically like, let me show you this other reflection probe here. That's the reflection probe that's rendering the mirror. And yeah, if I turn that option off, the mirror will be turned off only in the editor. If I go to the game, it's still being rendered. See, it only renders in the game, and yeah, it basically frees the GPU here. Like if it's not rendering on the editor, the GPU is free to do more more work, if you know what I mean. You can also find more information on the GitHub page of this project. You can basically see instructions on what exactly to do, how to get everything working. It's very easy, don't worry. You can see the documentation as well, like explaining everything that all the functions that the probe has, the methods, the properties, static methods, lots of things that you can do with it. It's all written here. And of course it's all MIT, so you can use it whatever you want. There's also like the example of like how I wrote that water shader here. It has transparency and the reflections mixed in, and it has this water foam here. You can take that water foam as well if you want. And yeah, this water shader here is like a good example on how to write a shader rendering from the texture that the probe is generating. So yeah, this is it. It's been a great learning experience for me, and I hope it's gonna be a good one for you as well. As I said, the project is MIT. You can take the code and modify it. You can study it. You can use it, the same technique, to make something else. I don't know. Be creative. Make good games out there and keep being awesome. Thank you for watching. Have a good one.